Hi, everyone. Welcome to 95th Stanford MedAI Group Exchange session. This week, we have Zeshan Hussain from MIT here with us to talk about his work on benchmarking causal effects from observational studies using experimental data. Zeshan is an MD PhD student in the Harvard MIT Health Sciences and Technology program. He completed his PhD in June 2023 at MIT WC as advised by Professor David Sontag, and is on track to finish his MD in 2025. His research interests span several areas, including deep generative models for healthcare, causal inference, and human AI interactions. Zeshan, thank you very much for joining us today. Before we start, do you have any preference on how you would like to take questions? Do you have designated breaks in your talk, or can we interrupt you in the middle?
Interruptions are fine.
Okay, thank you. So everyone, let's try to make this session as interactive as possible. And without further ado, let me hand it over to Zeshan.
Awesome. Thank you so much. Thanks so much for having me today. This is a really nice initiative. I didn't realize it was going on for a couple of years now, but Stanford's actually very near and dear to my heart. I did my undergrad there, and then after that, I did my master's there as well. Actually, I ended up working with Dr. Daniel Rubin, who was, I think, one of the organizers of this series. As it happens.
Yes, Dr. Daniel Rubin and two of his students, they started the series.
Oh, very nice. And I worked with Chris Ray as well. And so, yeah, excited to kind of jump into it. I am currently, so I'm going to be talking about kind of this work that I did during my PhD. And as Amara said, it's kind of titled Benchmarking Causal Effects from Observational Studies Using Experimental Data. And I worked on this towards the latter half of the PhD, the last couple of years, with a really wonderful set of co-authors. On the left is David, who was my PI, and then Mingjie in the middle, who is now an assistant professor in Taiwan at one of the top universities in Taiwan. Mike Oberst, who was a senior PhD student and is now a postdoc at CMU and is going to be an assistant professor at Johns Hopkins, and then Oker on the far right, who is a second-year PhD student now. So I'll begin with some motivation. And we're all pretty familiar with this notion of a randomized controlled trial. It's a very common study design, and oftentimes policymakers, clinicians, healthcare providers in general, they tend to rely on RCTs, clinical trials, to provide data-driven decisions on clinical management. And the reason is because, RCTs often have pretty distinct advantages. The main one being that if you kind of appropriately randomize people and you have sound design of the RCT, you can get an estimate of the causal effect of some intervention on an outcome of interest that's unbiased. And that's kind of the draw of this kind of study design. But of course, RCTs have their disadvantages. For one, they're pretty time intensive to design. And often the patient population that's enrolled into a trial is sometimes limited in scope due to strict inclusion criteria. And it may not necessarily just be the inclusion criteria. Sometimes it's not even feasible to enroll those patient populations for various reasons, logistical and otherwise. So, for example, back when the major trials were running, I think, for COVID to determine the efficacy of the vaccine, pregnant women weren't included in those trials. And so there was a paper that I'm citing here at the bottom left that was published in Nature Medicine that tried to estimate the causal effect of the vaccine on pregnant women from observational data. Okay. And so this transitions very nicely into another very common type of study, which are observational studies. And these consist of things like cohort studies, where a particular cohort is followed over time, and you're interested in kind of longitudinal outcomes, or cross-sectional studies where a cohort is looked at a particular time point. And one of the advantages of observational studies, canonically, is that they contain a more diverse cohort. And so you may have, in this, for example, you have like the blue folks and the red folks. But often there are issues within the observational study, such as unobserved confounding. You may not have measured all the confounders, which may make the estimation of an unbiased causal effect difficult or impossible. On the other hand, we actually may only have observational data in hand to estimate causal effects for underrepresented patient groups, meaning that for groups for which we don't have the highest quality evidence, you'll need to rely on observational data. Like, for example, in the COVID-19 example, you'll have to kind of figure out how to do your causal analysis properly and thoughtfully, and emulate a target trial from the observation data in order to find or estimate some causal effectiveness. So in the first part of this talk, I'm going to describe kind of what our main contribution of this paper is, that I have on the bottom right, which is a method that leverages RCT data or experimental data as a kind of sanity check for confidence on confidence intervals in the underrepresented group, as it were, that you get from the observational data. And these confidence intervals we show under some assumptions are provably valid in the sense that they should contain the true causal effects with high probability. So the ultimate goal here, kind of restating what I've said, is to indeed provide a valid confidence interval on the causal effect in this underrepresented group, whether it's the pregnant patient population in the COVID example or otherwise. And we can formalize the causal effect in a straightforward way. And this is something that maybe some folks have seen, which is what I'm calling here the group average treatment effect. And this is defined as the expected difference in potential outcomes on this treatment and control in a specified subgroup. And the expectation is with respect to the distribution of people in this group I. And so the shorthand, I'm going to refer to this effect as the gate. Okay. So to kind of depict our goal in a more visual way, I have here on this axis the true causal effect in the subgroup, which is plotted as this white diamond. And our estimate of the effect is indicated by this tau hat. And our goal is going to be to output a confidence interval that contains the true causal effect with some high probability. And so something like a 95% confidence interval should contain the true value at least 95% of it. So at this point, I'd like to provide some context as to how a confidence interval on the causal effect in an underrepresented group might be currently reported, or how estimates from observational studies might be aggregated and gathered and reported to the researchers and scientists. And the key point here is you actually may have multiple observational studies from which slightly different interval estimates are given. So one example is if 3 different hospitals provide 3 different data sets or registries for a particular population. And naturally, you may have 3 different interval estimates for the causal effect, and in the underrepresented group that come from these 3 separate observational studies, due to the fact that maybe in one hospital you are able to measure more confounders or more variables than in another hospital. The nature of the management and the nature of the intervention might differ amongst different hospitals and so on. And so it may be the fact that the interval estimate that you get from one of these observational studies might be biased for various reasons compared to another observational study. But the issue is current approaches to meta-analysis of these observational studies assumes that all of these studies are valid, e.g. that none of them have confounding, and that you are kind of aggregating unbiased estimates to come up with a final kind of confidence interval, estimated causal effect. And so the first kind of key intuition that I'd like to kind of page in for people is that in this work, we assume that at least one study is valid, which is naturally a weaker assumption. Okay. So now we're kind of ready to jump into our approach, and I'll describe at a high level what we're doing. And I've termed this extrapolated pessimistic confidence sense, and it'll become clear as to why this is a natural name for this method. The ingredients required are effect estimates, a set of effect estimates from a randomized trial, and a set of effect estimates from multiple observational studies. Now, the point is in that both of these studies will have group average treatment effects of gates for several subgroups. So in this case, it'll be for these two subgroups in the observational studies and these two subgroups in the RCT with the same kind of subgroups in both studies, right? And there'll also be some subgroups that only exist in the observational studies, such as the pregnant population, as indicated in the picture. And so these are the overlapping groups, and this is kind of the one that's only in the observational study. And again, our main assumption is that at least one observational study provides valid estimates and confidence intervals across all the subgroups. And the approach at a high level has two steps. The first step is validation of each observational study on the shared subgroups, i.e. the subgroups that are shared between the observational data and the RCT data. And then the second step is what we're calling pessimistic aggregation of these results across the studies that have been kind of filtered in or validated from the first step. And I'll explain what pessimistic aggregation means and why it makes sense. So how does this work? Well, imagine now visually, we have the interval estimates from 3 separate observational data sets as shown here. And this is for, let's say, the pregnant population. Naturally, this is, this is the underrepresented group. This is the population for which we care about having an estimate, and we don't have an RCT for this population. And so this is kind of we're going to have to like rely on sort of these estimates from the observational study. And well, how do we actually get these estimates? Well, we can do some type of causal analysis where we've drawn out our causal graph. We've identified the confounders of interest. We can then identify the causal effects given the graph, and then estimate the effect using some standard estimator. Okay. And then we'll have these 2 other subgroups for which we do have the causal effect estimates of the outcome in an RCT. And naturally, we can sort of do the same thing. Estimate the causal effects in the observational studies for both of these subgroups as well. And now the key point here is that what if we compared these effect estimates via hypothesis testing? Sorry, it's kind of cut off here at the right, but this just says comparison via hypothesis testing. And we're asking the question, well, do these estimated effects agree in the shared subgroups? And intuitively, if they do agree, well, that's good. And we can sort of say, okay, it's nice that they agree. But if they don't agree, then we may want to flag this study and remove the studies that don't pass this test. Now, there are 2 key subtleties that I've kind of glossed over that I'd like to bring up, because it's not as straightforward as just doing a hypothesis test between kind of 2 effect estimates. There are 2 subtleties. One is that if you use like something simple like a z-test or even t-test, you have to kind of prove that the estimator that you use is asymptotically normal. And so that's not necessarily straightforward in the group average treatment effect setting. And we deal with this extensively in the paper, trying to provably show this. The other subtlety is that this only works if kind of your let's say there may be differences between the observational population and the RCT population that isn't captured by the group indicator. And so a naive comparison of the observational study effect and the RCT effect wouldn't work because you're not comparing apples to apples, right? So the most intuitive way to think about this is differences in the effect modifier distribution between these 2 populations. So for example, let's say you're in a subgroup, and maybe the subgroup of interest is like people who have renal disease or CKD or something like that. You could, in this subgroup for the observational study, you could have, in this particular subgroup, you could have 25% men and then 75% women. And you'd average kind of the causal, the treatment effects for each person in that subgroup, and you'll get some number, and that'll be the causal effect for the CKD group. For the RCT, you could be interested in the exact same subgroup, the CKD subgroup, but you may have 75% men and 25% women, right? And you'll do the average, and you'll get some number, and likely, if the causal effect is actually different for men and for women, even if if they were 50-50, it would be the same, but because of this difference in distribution in gender, they're going to be different, right? So what I'm saying is you have to correct for kind of these differences in the distribution, in the effect modifier distribution. In this case, an example I gave would be gender. Okay. And so kind of you in essence, the way that you would correct for it is you have some target population. And in this case, we're going to use the RCT population as the target population. And you'd have to kind of express the causal effect in the observational study with respect to the target population or the RCT population. And this kind of transportation to a target population is known in the causal inference literature as transportability. And there are many folks who have worked on this. And there exist, estimators, at least in the average treatment effect setting, where under mild assumptions, you can prove asymptotic normality, which we'll need for hypothesis testing. It wasn't straightforward, or at least in our kind of digging through the literature for like the group average treatment effect at the subgroup level, it wasn't straightforward how to like extend those asymptotic normality results to our setting. So we do that in the paper. We kind of extend it and prove that we have asymptotic normality for the group level estimators as well, which is necessary for the hypothesis testing. So anyway, those were subtleties that I just wanted to bring up. It's not necessarily important to get all those details, but I just wanted to flag that in case people had questions about it and wanted to kind of look at it in the paper. Okay. So once you've done this, there's another caveat, another challenge, which is that passing the hypothesis test doesn't guarantee that these studies are free of confounding. You might think, oh, like, I haven't rejected this test, or rather this study, I haven't flagged it, we're good to go. The issue is that you actually may fail to reject due to small sample size or a lack of power to detect the violations in the first place, okay? And the way that we deal with this is, if we kind of zone in or zoom into the kind of underrepresented group of interest, the way that we deal with this is, let's say you have the confidence interval from each of the studies that have passed your initial test. We can bypass this challenge by this idea of pessimistic aggregation of the results, whereby as long as one of the observational studies that isn't rejected is correct, then we can simply union the confidence intervals from the studies that remain. As long as we have an interval that contains the true causal effect, the union of the intervals will still give us an interval that contains the true causal effect, even if there are other intervals that we're aggregating that are completely wrong, right? So this is what I mean by sort of pessimistic, like unioning these intervals is pessimistic in its nature. And so in other words, now the thing is, if you do this, you might get a super wide interval that'll like trivially cover the true causal effect, but like maybe it's like really wide, and so it's not as informative. But the trade-off we're choosing to make here is that we'd rather give you an interval where we're sure that the causal effect is covered, rather than a super narrow interval where we actually don't have like a theoretical guarantee with respect to the coverage of the true causal effect. Okay, so that was kind of the intuition behind the procedure. And the next part is like some experimental results, but maybe this is a good time to pause and see if anybody has any questions.
So I can ask a question here. The assumption is that you already know your subgroups of interest.
Yeah, so
like on the basis of
yeah, a great question. Yeah, so the assumption here is also, or not even assumption, it's kind of a necessary thing that you need in order for this to for this algorithm is that you need to pre-specify your subgroups. Yeah. And we'll actually, in the second part, we'll relax that and we'll kind of discuss a method where we don't need to do that. Yeah, it's a good question. The other thing that's related to this point is that because you have multiple subgroups, you're actually, in this first step, you're technically running a separate test for each subgroup, for each observational study. So you'll have to also correct for multiple hypothesis testing because you're kind of running multiple tests at the same time. So it's
and then to reject a certain observational study, it's like if it fails for one group, you can reject it, or if it fails for all group.
Yeah, fails for one group. So it's a pretty conservative kind of
okay.
rejection.
Makes sense.
Great. So we, of course, ran some simulations in the beginning, and then we kind of tried to jump into real-world data to see how this would play out. I'm just going to hide the meeting controls. Let's see that. And so we use this data set from the Women's Health Initiative. And this data set is actually a randomized trial and an observational study that was done in parallel from 1993 to 2005. And they studied the effect of hormone replacement therapy on several outcomes in postmenopausal women. So this was only postmenopausal women, and they studied the effect of HRT on things like cancer outcomes, breast cancer, all types of cancer actually, so several set of outcomes. This is really nice because this is one of the only things that I can think of, at least publicly available, that has both randomized trial data and observational study data at an individual level. It's available for researchers through BioLink. And you just have to submit like a very simple application, and they're very nice about sharing this data with researchers. And we also have pre-processing code available for this that I have to make public when I don't have to be in the OR anymore. So I'll do that soon. Okay, so in order to run this experiment, one kind of practical thing is we need to first ensure that we can replicate the results of the RCT with the original observational study via target trial emulation. And we can treat that original study as quote unquote the unbiased data set. And then we'll simulate additional data sets with artificially induced selection bias. And this was mostly to simulate the notion of having multiple observational data sets with some of them being biased. And the way that we introduced selection bias was out of the set of people who were not exposed to the treatment and did not end up getting or experiencing the event, we drop each person with some probability P. And again, we treat the original data set as the unbiased one, since we're able to kind of successfully replicate the trial results with it. And then we remove one of these subgroups from the RCT and treat the estimated effect for the subgroup from the RCT as kind of the ground truth. And then we can obtain confidence intervals on the causal effect on the underrepresented group, and then assess coverage of the estimated RCT effect to evaluate it, because we've taken this estimated RCT effect as the ground truth. And this is done for some like randomly selected set of subgroups, and we can kind of repeat this on different splits of subgroups, and we end up doing 600 runs of this. And essentially we get kind of a list of relevant covariates, and we can take pairs of those covariates and generate like 4 subgroups, for example, from those pairs, and then we repeat that kind of randomly for different pairs of interest clinically 600 times. And each of these pairs is kind of a separate run, each of these splits. Right. So in terms of the results of the experiment, the two kind of evaluation metrics we use are coverage and length. Coverage refers to the percent of time that in each of these runs we actually contain the RCT estimate. And the length refers to the average length across all these runs of the confidence intervals. Naturally, we want really high coverage, and we want it to be as precise as possible, so very narrow. And so we can start with kind of an oracle, which is this oracle baseline. And we're going to only use the estimates from the original observational data set. We're going to kind of tell the algorithm that all these other ones are biased. This is like the kind of unbiased one, and you only need to use this one. Remember, we had kind of a set of artificially biased data sets, and the algorithm itself doesn't know which data sets are biased, but the oracle, we kind of hard code that this is the one that's not biased. And so if we run a standard meta-analysis procedure on these observational studies, where some of them are biased and one of them is not, we see that we get pretty bad coverage and suboptimal length of the confidence intervals. And this makes sense because we've assumed that all the studies are free of bias, which has led to kind of this poor coverage. And then we report the results of a variant of our method, which assumes that the studies that have passed the hypothesis tests that have been validated are free of bias. Now, remember, before for our method, we didn't assume that. We kind of did this pessimistic aggregation. And here, we kind of try and take the narrowest interval possible based on sort of the observational studies that have passed the test. Naturally, we get a pretty good length. It's very narrow, but we suffer in terms of coverage. And so our method kind of like has this nice balance of, getting good interval length, like narrow interval length, but not sacrificing coverage, which is due to the fact that we have this kind of union of the validated observational study intervals. As an aside, maybe people are wondering why this is slightly higher than the oracle, the coverage. It's due to the fact that the intervals we output for our method is slightly wider, just because of the kind of Bonferroni collection we have to do for the multiple hypothesis testing. And so it was like an alpha over 4 instead of like an alpha over 2. So it's like just slightly wider. That's fine. Okay. So just to recap this first part, the idea is that we have randomized controlled trial data, strict eligibility criteria. It's not representative of all patients. We also have observational studies that are more representative of all patients, but maybe subject to confounding. Can we use RCT data to kind of as a sanity check in our procedure of aggregating evidence and coming up with valid confidence intervals and the causal effects for the underrepresented subgroup? Okay. Now, we use the RCT to relax the assumption that all observational studies are unbiased. And we can do that because we have this extra kind of information. Okay, so I mentioned this notion of hypothesis testing comparing these effects estimated from observational data and the RCT effects. When we had finished the initial paper, there were a lot of these open questions, kind of really exciting future directions to pursue. And this is one of those open questions that we decided to pursue first, this hypothesis testing piece. And the question really was, can we construct a higher powered test to reject observational studies that were biased without going overboard, without kind of rejecting everything for minute differences? And to provide more context as to why we might want to do this in the first place, it's useful to think about the drawbacks of the previous approach that I just presented. And so one of the core ideas in the previous approach, as Amara had asked about, was that you had to select a pre-specified set of subgroups that a domain expert might be interested in. And then you have to see if the observational study lines up with the RCT in these specified subgroups. And that might be useful in some cases. Like you might have a set of subgroups that you're already interested in, and this is kind of fine. But unfortunately, in other cases, it may not be okay. And you may want to kind of circumvent that and not have to do that. And of course, because you're selecting the subgroups and having to run the hypothesis testing multiple times, you're going to need to correct for multiple hypothesis testing. And it would therefore be nice to kind of find these automatically. And so these are two of the drawbacks of what I'm calling the gate approach. This is kind of the first approach, the subgroup level approach. But if we even take a step back before like thinking about subgroups, like we could also just compare the average treatment effect across the RCT and the average treatment effect across the observation study. That could be a like first cut at comparing these things after transporting to a reference population, assuming sort of you have you're able to do that. The issue is that this could lead to false negatives. You may not reject when you want to, and an intuitive way to think about why this might lead to false negatives is think about if you can think about the cape function, sort of a more granular sort of function, and maybe I'll just draw this out so it's more clear. You could think about the conditional average treatment effect. Let's say there's like a one-dimensional covariate here. And in the RCT, you could have like, I don't know, something that looks like a sine wave. And in the observational study, this might be like this, right? Where if you average this across the population, both of these will have the same ATE, meaning it will be 0. But in this subgroup, i.e. when X is less than this threshold, the conditional average treatment effect, or even just if you average this, is going to be completely different. So if you just compare the ATEs, you're going to potentially lead to false negatives. Hopefully that makes some sense. The other issue with this is that there's also no explanation for rejection. It would be nice if you kind of do reject in the ATE case. It'd be nice to sort of say, okay, where in the covariate space is sort of the region of issue where the observational study might be biased. In the average case, you kind of lose that information. Okay, so we'd like to develop a method that overcomes some of these barriers. And to do that, we're going to introduce some terminology, which is actually very relevant for the last part of the first part of the talk. But I wanted to shield you from like the technical language as long as possible. But now, like internal validity and external validity are in the title of the paper, so now we have to talk about it. So we'll talk about it. And so, what is this notion of internal validity? In the transportability literature, it's kind of this ability to estimate causal effects that are unbiased, to estimate unbiased causal effects within the study population. So within the, if you have an RCT, within the RCT population, can you like estimate the causal effect in an unbiased way? This assumes that you've done randomization appropriately. This assumes that, you have no like confounding for some reason because of efficiencies in your randomization, whatever the case may be. You can also think about internal validity in the setting of an observational study. Of course, it's a little bit more difficult because in that setting, you have to assume that you've measured all your confounding variables. You have to, the causal effect itself has to be identifiable. There are other assumptions. And the point is that often this assumption and kind of the sub-assumptions that come under it are untestable from data. The other term that I wanted to introduce is this notion of external validity, which is the ability to generalize the causal effect estimates to a different context or population. And formally, this is that an internally valid effect estimate is unbiased for the causal treatment effect in a different setting, such as a target population of interest, okay? And so this is, as if you're kind of connecting the dots, this is related directly to the causal effect being transportable to another population. So I mentioned this notion of kind of transporting the causal effect in the first part of the calculated reference population. In order for you to do that, you have to assume assumptions that come under external validity.
Zeshan, can I ask a question here?
Yeah, sure.
External or target population, in this case, it's similar to the example that you were giving earlier. For example, pregnant population, which was not part of the original RCT. So the external validity means that you can generalize causal effects to such an unseen population.
Yeah, well, I think here it actually means more of, it's more general. It's just like a different population. There is a subtlety in that you can't have like a, we'll talk about this, but like this is in the case where all the subgroups are still shared, but maybe the effect modifiers are slightly different. And so in that case, the populations will be different. So it's referring to being able to generalize to that different population. So from like the from the observational population to the RCT population, for example. So it's a more general, it's more general in that sense.
Okay, we're not talking about a particular subpopulation that was not part. It's just a different population.
Yeah, just a different
overall. Okay.
A different population overall.
Okay.
Exactly. Yeah. Okay. So as I mentioned, both of these concepts have their own set of causal assumptions and are only applicable when these assumptions are met. And to reiterate, the tricky part here is that none of these assumptions are directly testable from data. And as a kind of, foreshadowing, what we're going to try and do is sort of think about whether or not there are implications of these assumptions. If we were to assume they're true, do these assumptions have any implications statistical implications that are testable? And we're going to try and test those implications instead in order to kind of go around this problem. Okay, so our goal in this part of the talk is going to be a little bit more focused than the first part. We're not going to be worried about like a separate subgroup that isn't shared. We're going to only be worried about kind of the shared population, or at least the shared subgroups. And we're going to try and sort of focus in on using experimental data as a form of validation to falsify or benchmark, at least, assumptions of external and internal validity in observational studies. And this is very similar to what we did in step 1 of the previous part. Okay. And in particular, if you kind of think back to this slide, and I had this like question where I said, oh, do estimated effects agree in shared subgroups? Can we do hypothesis testing, blah, blah, blah. That's like a very general thing, and I didn't go into any of the details. I hadn't really unpacked it, what I meant by that. And so we're going to try and unpack that a little bit more in this part. And the first thing to do, which we've kind of already done, is we hadn't really formalized this idea of bias. Like, if an observational study is biased and we're rejecting it, like, what does that mean? And that was the purpose of introducing the notions of internal and external validity. And so simply, if an observational study doesn't meet those assumptions, or for some reason those assumptions are violated, then it's biased. Okay, so that's sort of the reasoning for bringing in those terminology. Okay, so now we can go back to this slide. And our goal here is coming up with a higher powered kind of comparison test, such that if an observational study passes this test, we have more confidence that the observational study may not be biased. So to elaborate, suppose that we have one observational study on the left, and one RCT. Okay, the observational study is actually depicted on the left, and with this study we can produce a set of treatment effect estimates with respect to the RCT population, assuming that these effects are transportable, assuming kind of external validity. So we're going to assume that for now. And so again, the high level point here, we're going to assume these assumptions that I brought up. We're going to think about whether or not they imply something that's testable from data. We're going to test those implications, and if we If there's something wrong, then we know there's something wrong kind of upstream. There could also be something wrong downstream. So we have to kind of sort of make sure that we're well specified in our modeling. But if we're well specified in our modeling, then we know it's something upstream. Okay. So the other point is we also have RCT data, and we can produce effect estimates from the RCT data as well. Okay, so now we have effect estimates with respect to the RCT population from the observational data, and we have effect estimates from the RCT. And we have two sets of estimates. And under these assumptions of internal and external validity of the observational study, these two sets of estimates should be estimating the same causal quantity, right? And they should now be comparable. And so leveraging this fact, the statistical test that we'll come up with will essentially serve as a test of the internal and external validity assumptions of the observational study. Okay. Beforehand, in the first part, to do this testing, we essentially use like a simple z-test under the hood after proving kind of asymptotic normality of the resultant estimators. But now we're gonna hopefully try and do something a little bit better. Okay. So in coming up with this algorithm, this test, what are some of the desired properties? Well, one, we want something that has high power. In other words, when either the internal validity or the external validity of the observational study is violated, we want to reject or flag the study with high probability, right? We want high power. Now, notably, we won't be able to tell, even if we do reject, which one of these two sets of assumptions is the one that's violated. It could be both of them. It could be one of them or the other. But we'll know that something's wrong. The second part is we want to control type 1 error. And, naturally, this means that given that both of the assumptions are met, we want the rejection rate for the observational study to be controlled at a nominal level alpha, 0.05. So simply put, like we want to make sure that we don't reject in that setting. Right? And the third thing is we ideally like an explanation of why we rejected. So for example, we might be able to know, or we want the algorithm to output that, when it rejects the observational study, it should give some sort of explanation, like, the causal effect estimates from the observational study tend to be positively biased compared to the RCT for older male patients. And so, then you can kind of, this is useful because you can go back and you can look into the subpopulation, kind of probe into the reason for why there's bias. And as a practitioner, this might be useful for you. Okay, so how do we actually do that? Well, kind of the core contribution is this translation from these causal assumptions to this statistical quantity. Like, what are we doing here? Well, we've shown how these assumptions of external and internal validity can be converted into this set of what are called conditional moment restrictions, which can be tested using existing techniques with theoretical guarantees. And so that's nice. And what's the high-level intuition for this? Well, I'm going to give it to you now. We're going to revisit this at the end. Okay. Which is, if we're able to convert these assumptions into these CMR, these conditional moment restrictions, then we can use a test statistic that will, by construction, find regions in the covariate space where there's a large difference between the observational study and RCT in terms of the case. I.e., like when the test statistic is large, we're able to sort of see where the Kate signal difference is large in the covariate space. Okay, and we leverage the theory behind these test statistics, which I'll kind of introduce them. They're called maximum moment restriction tests, to provably show that these will have sufficient power and nominal level to have a controlled type 1 error, meeting the property that was two of the three desired properties of the algorithm. Okay, so we'll revisit this intuition at the end. So just hold on to kind of this diagram. So briefly, what is a CMR? It just essentially refers to the conditional expectation or the conditional mean of a function of the data. And the restriction part of this is saying that this conditional mean is almost surely equal to 0. So equal to 0 in this probabilistic kind of almost surely sense. And that's all it is, okay? And note that the set of CMRs, the idea is that this will encapsulate the difference in Kate estimates between the RCT and observational study. That's sort of the idea. And again, I'll revisit the intuition for why that's the case at the end. Okay, so now we can move on to formalizing our assumptions and translating them to this set of conditional moment restrictions. That's what I'm going to show you. And then I'm going to show you the intuition for why that works. And then we can look at maybe an experiment if we have time. So we're going to start with the internal validity of the RCTs. Because actually, I guess I didn't mention this before, one of the things that is necessary here, the internal validity of the observational study, the external validity of the observational study, you have to assume these are true. But the RCT itself also has to be internally valid. You have to be able to estimate unbiased treatment effects from the RCT. Typically, people are more comfortable with kind of assuming this, especially if you're the person who's designed the randomized controlled trial, kind of what if it's a sound, design, if the randomization happened appropriately, if people were, adherent, etc. You kind of have an idea, and you'll know if the causal effect you get is actually, or that assumption is a little bit easier to make, arguably. But naturally, if you reject it, could be that the RCT is not internally valid. But what I'm saying is that that's less likely. So what are the assumptions that go into the internal validity assumption for the RCT? It consists of three things. These are things that people are typically familiar with. The first assumption is intuitive, which is that the treatment is assigned following a randomized process, essentially, and that we have ignorability of the treatment assignment, where the covariants don't affect the assignment of treatment and don't confound its effect on the outcome. Right? Another assumption is that we have fixed probability of assignment. Often it's 0.5. And the third assumption is that we have consistency, which means that the observed outcome actually corresponds to the counterfactual outcome. And then similarly, we have internal validity of the observational study with some of the main differences being that instead of ignorability, we have conditional ignorability, which states that given the observed variance, i.e. the observed covariates, the treatment assignment is actually ignorable. And another kind of equivalent way to say this is that there's no unmeasured confounding. So that's, I guess, an easier way to think about it. And of course, we have the consistency assumption as before, and then we have positivity, which means that for each type of patient, there's a non-zero probability of this patient being kind of observed to have one intervention versus like the control versus another intervention. Now, again, internal validity of the observational study isn't enough, since we still need to be able to compare causal effects between the observational studies and the RCT. And in particular, as we've discussed before, there may be differences in the effect modifiers in the two populations, which prevent direct comparison of the causal effects, right? So like this is kind of that difference in the male to female ratio as an example, and you have to kind of correct for that. And so there are certain assumptions that you need to make in order to be able to do that correction is the upshot. And these assumptions are related to the assumptions of external validity in order for you to be able to make that transportation. The first assumption is this notion of mean exchangeability of contrast, or exchangeability of conditional average treatment effects. This is kind of the definition here, which is the expected difference of counterfactual outcomes under treatment versus control. And because the conditional, this is kind of the assumption is that the Kate under the observational study is equal to the Kate under the RCT. They're exchangeable. And this is kind of equivalent to this mathematical expression where the indicator here refers to either the RCT or the observational study. S equals 0 is the RCT and S equals 1 is the observational study. What you really need to know here is that this assumption is encapsulating in kind of this mathematical form the assumption that you don't have any unmeasured effect modifiers. So in the case, let's say you have a difference in the proportion of males and females in your observational study versus your RCT. All this is saying is that you better make sure that you've observed gender. Like you can sort of say who's male and who's female. Otherwise, you won't be able to correct for it. That's basically what this first assumption is saying, that you have no unmeasured effect modifiers. And the second assumption is this positivity of selection, which means that the type of patient, if they have a non-zero probability of being in the RCT, then they should still have a non-zero probability of being in the observational study. So this ensures that we have enough support to use this notion of transportability to transport the treatment effect estimate from the observational study to the RCT population. Okay. I have 7 minutes to go through kind of like the procedure, and I think I can do it. Do people have questions about kind of what these assumptions are, what they mean? So
I don't see any questions in the chat, so maybe we can keep them for the end. You can go through the process first.
Okay, yeah, sure. Yeah, maybe I'll just go through the process, and if we have time, we can look at the experiment later. Okay, so what does the falsification procedure actually look like? So with these assumptions in tow, the assumption of internal validity of the RCT and then internal and external validity of the observational study, we can construct a set of vectors of unbiased, instance-wise conditional average treatment effect signals from the observational study and the RCT. And so for the observational study, we'll indicate that via psi1, and for the RCT, we'll use psi0. And because kind of by this assumption that we had, it implies that psi1 and psi0, if we're assuming all these things, it implies that psi1 and psi0 each estimate the same causal quantity, the same conditional average treatment effect. And so this implies that the conditional expectation of the difference in these Kate signals should be zero in an almost surely sense. With respect to this joint distribution of the covariate space, which is the joint distribution of the covariates across both the RCT and the observational study. Okay, and this is essentially the set of conditional moment restrictions we are using in our test. This is kind of by definition what it means. So now how do we actually construct these estimators? For the Kate signal from the RCT, we can use a standard inverse probability weighting style estimator. And under this assumption of internal validity of the RCT, this we prove in the paper is actually an unbiased estimator for the Kate and the RCT population. So all the proofs for showing that these are unbiased estimators, assuming these causal assumptions are shown in the paper. And then for the observational study, because we have to deal with this kind of transportation, and now we also have to deal like the estimation within the observational study itself is a little bit tricky. We kind of use a fancier estimator, and it ends up being a doubly-robust transported estimator to account for kind of the high-dimensional covariates as well. And under the assumptions of the internal and external validity of the observational study, we prove that psi1 is an unbiased estimator for the same causal quantity, the conditional average treatment effect in the RCT population. Okay. And so now if we let psi equal the difference in these Kate signals, this implies, assuming these assumptions are true, this implies that the conditional expectation of this signal, of the difference in these signals should be zero almost surely. Now, this is actually our conditional moment restriction. Like this is our set of conditional moment restrictions. We need to be able to test it because this forms our null hypothesis. Our null hypothesis is that these assumptions hold and that it translates to this statistical kind of quantity, this object. We want to test it somehow. It turns out that this is hard because these set of conditional moment restrictions, they imply an infinite set of unconditional or marginal moment restrictions. And this is via the law of iterated expectations. And what's nice is we have a previous result from Wandet et al., Kukumo Wandet, which was published in 2020, that basically states that if you constrain this set of measurable functions to be an RKHS with some nice kernel, then you can actually test this null hypothesis using the maximum moment restriction as your test statistic. So they basically show this in this paper. This is the maximum moment restriction, kind of by definition. And so we can ensure that the top here is equivalent to this bottom expression. And why this is nice is because in this paper as well, this test statistic actually has a nice closed form expression that we can analytically compute from data. And so that's kind of the point. And so if we kind of dig deeper into this test statistic, we're trying to maximize the square of the expectation of psi times f of x. And this means that if psi, which is this difference in the Kate signals between the observational study and the RCT, has a large magnitude and is positive, what will maximize this quantity is if f is positive as well. And when psi is a large magnitude is negative, f should be negative to maximize the test statistic as well. And so f will kind of mimic when psi, like the magnitude of f will tell us sort of the regions or where psi is, the signal difference is very large and where the signal difference is very small. A nice kind of byproduct is that we can actually look at this f. And that's why we can look at particular regions of this f where it's very large or very small. We have a closed form expression of the maximizer f star, and we can visualize it to introspect to exactly where which regions are small and which regions are large. Okay, so I'll stop there. This is kind of semi-synthetic studies that show sort of that we're maintaining kind of the right type 1 error. Oops, I don't know why that happened. Sorry. I don't know what happened to the computer. Yeah, that we have the right kind of level, and we have kind of better power than other tests. And I also show how we can visualize this maximizer to look at particular subgroups or covariate spaces that have high bias. Okay, so I'll stop there and maybe I'll take questions. And as a concluding statement, I think that the purpose of this talk was to give you kind of methods that are more formal in benchmarking causal effect estimates from observational studies using experimental data. So that was the thing.
Thank you very much, Zeshan, for this interesting talk. So before we move on to questions, I think we should give our presenter a virtual round of applause. And then if you have any questions, you can just ask or type them in the chat. And since we are over time, if any of you have questions later, you can contact us and we'll put you in touch with the presenter. And this talk will be put up on YouTube. If nobody else has a question, I can ask one question. Zeshan, so I understand with this method, you can identify the region of covariates where the assumption where there's a large difference between randomized controlled trial and observational studies. Yeah. Is it supposed to, I mean, the purpose of this experiment is to just reject that observational study, or is there a way to kind of correct that study? I mean, what if you have identified a region, for example, in your example, people who drink or people who don't drink, they have like a difference. So could you change your observational study data to be, I don't know, compliant with the RCT, or you just have to reject that observational study altogether? Yeah,
no, it's a great question. I think the idea behind this kind of method is not to sort of, once you, I mean, it's hard to even use the word reject, actually. Like the more, I think we had a conversation with some folks here at the public health school, and I think they recommended using language like benchmarking and flagging the study, because it's not like you're going to ignore the study after you kind of flag it, right? Like it's more about it's more about like, okay, we're going to flag it. We're going to sort of tell you, here are some regions where, there's some difference. And now, as kind of like the healthcare providers, clinicians, statisticians, we need to do some digging and to like figure out why that's the case. Which of our assumptions do we think might not hold anymore, right? It's almost like this additional sanity check, additional kind of validation. Whereas now we don't really have that, right? We kind of hope that our causal assumptions are reasonable.
And one other basically question. So in this covariate region, and I just want to connect it with the first part of your work, any subgroup of population that is kind of different between RCT and observational study, for example, pregnant women. Is this supposed to be covered in the same covariate space, or is that subpopulation can just lie outside of the space?
Yeah, I mean, as long as the subgroups are shared, actually,
subgroups are shared, okay.
The RCT and observational study, so the pregnant population wouldn't actually be something that would be relevant here because it's not shared, it's only in the observational study.
Okay.
So this is almost like a more powerful step one of the first part, and then step two would be kind of looking at like the underrepresented group and so on.
Okay.
But you're right. Like ideally, this would kind of capture all the things that we would have pre-specified. Like if there was a difference in a pre-specified group, we would ideally like to capture that in this group as well. And I believe we might have some simulations in the future. I would have to double check, but it's a good experiment to kind of run to sort of make sure that we recapture that.
Okay. Thank you very much, Zeshan, for this interesting talk. If anybody has any further questions, we'll put them in touch with you.
Awesome.
Thank you very much for joining.
No problem. Appreciate it. Thanks for having me.
Yes. Sorry about that email mishap. I only realized that emails are not being delivered this week. Yeah. Sorry about that.
Not at all. Okay. Take care.
Thank you very much. Bye.
Bye-bye.